So let's kick off. So last week we tried to learn something regarding population and sampling. So just to give you a quick overview again and connect the dots from the past week. Population is basically the universe of my selection criteria. So if I'm selecting number of students who go to school, or number of 17 years old who go to school in Australia, for that matter I said Victoria, then that is my population, because it is a really larger number. But then if I ask how many of them out in Victoria go to school, then what do? I have to literally go and count each and every house of Victoria and see how many of them are there 17 years old and going to school, which is time consuming. I shouldn't say impossible, but that's time consuming, and it could be a humongous task to do. At times I might not be able to cover the population itself, right? So in that case I use something called a sample. So out of all the suburbs, I'm just giving you an example here, out of all the suburbs I pick up one random street and I pull 17 years old out of it, and let's say I was able to pull out 1,000. So that is my sample. That is my sample size, which is represented by n. Now out of this 1,000, let's say I found that 600 go to school. Then I introduced a new term called sample proportion, which is represented by the letter P, caret, P, hat, whatever you want to call. And my sample proportion is the ratio of how many going to the school over the total count. Mind you, this is not the probability. Depends upon what I'm measuring. It could be probability, but for the sake of simplicity, we'll not confuse it and we'll call it as sample proportion. So that's called sample proportion. Now, this gives me a fair estimate that, all right, 60% of my population of 17 years old might be going to the school. So that is how I make predictions for my population. Now, let's take a smaller number and understand very quickly. Shall I take this off the board, please? Yeah. Let's quickly now understand what are we trying to achieve out of this sample proportion. So far in the world of probability, what we have learned is we learned the discrete random variable. We learned the discrete random variable. In the world of discrete random variable, we learned a few things. We learned when my n, which was not the population proportion or not the sample size, but in general, my universe. When my n was a small number, let's say a bag of 10 balls with 6 red and 4 blue balls. 6 red, 4 blue balls. My n is a small number. I used to find the probability in this case using the selection, and I say NCX. I say, what is the probability if I draw 3 balls out of this bag of 10 balls? What is the probability that I get 1 blue ball? So how do I used to do it? I used to say, all right, I need 1 blue ball out of the 3. So what are my possible choices? I say red, red, red. That means no blue ball. And then I say 1 blue ball. So that means I'm not taking the red. 1 blue ball could be red, red, blue, red, blue, red, blue, red, red. Right? And then I used to say, all right, I can find the probability. So the red is 6 on 10 times 6 on 10 times 4 on 10 plus 6 on 10 times 6 on 10 times 4 on 10 plus, and this is with replacement. Let's say this is with replacement. 6 on 10 times 6 on 10 times 4 on 10. Basically, that's the cube, right? So that is when my n was a small number, I used to deal with it, right? With this way. Now, when my n became really large, then I started using something called binomial. What is binomial? Binomial is when your measure of success is getting a blue ball and rest is all the failures. So what do I used to do? The formula was NCX P times X 1 minus P of n minus X. Correct? Where X is the value of the discrete random variable. Moving further, we also learned something called normal distribution. And the normal distribution used to be a curve like this. And that was when we were talking about the continuous random variable, right? We learned one thing in the normal distribution was when your n is really, really large, your binomial distribution starts to throw trends like normal distribution. So you can approximate binomial using normal. So in this world of sampling and estimation, now we will make use of the discrete, we'll make use of the binomial, and we'll also make use of the normal. But not on any discrete. What will be my random variable? My random variable in this case, in this world, will be the sample proportion p hat. So now my random variable will be the sample proportion. That is what this topic is going to do with whatever we have learned so far, right? Now, take this off the board again. By the way, that blue and the red ball topic, there was another way of doing it. So you had like 6 red balls and 4 blue balls, and I'm selecting 3 balls at random. So what is the probability that I get 1 blue ball? In how many ways can I select 3 blue balls out of the 10? Can I say, is it not? That's the selection in my universe. And I need 2 red out of 6. So 6C 2 times 1 blue out of the 4. That would have given me the probability as well, rather than thinking about red, red, blue, red, blue, red. I mean, anyway, whichever, but still, this is when your n is small, right? So now, let's talk about I'll take an example from the book, and that'll quickly make more sense. So let's say, same story, and now I have, I'm just taking it so that I don't get confused. So I've got 10 balls again in my bag, and this time I have 6 blue and 4 red. So this was the example that I did last time. I'll quickly, so I've got 6 blue and 4 red balls, and I am asked to, I'm pulling out four balls without replacement. I'm pulling out 4 balls without replacement. So let's see, first of all, what is my sample proportion for the blue balls? Now this is my population. Now I draw a sample out of this population. And let's say the sample is of 4 balls. Now I'm using the word sample intentionally, right? So I have taken the sample of 4 balls. Now that means my sample size is 4.